There we go.
Okay.
Harold Locke is on.
Okay. I'm not seeing anything on YouTube yet.
It takes a minute.
Okay.
And Book Davies is on.
Okay.
Let me. He says he got his 2-inch Explore Scientific diagonal today. Woohoo!
Yay.
Okay, everybody, how's my volume sound before we
Volume
get?
sounds great.
Sounds good to you. We'll see how it sounds to the audience here.
Okay. I'm still looking on YouTube. I'm not seeing it. I'm going to refresh.
Yeah, hit refresh.
Oh, there we go. How do you know episode 4? Still looking on YouTube. I'm not seeing it. Oh, goodness. I'm getting.
You have to turn down your YouTube volume.
There we go. How do you know episode 4? And there, I've killed my volume.
Perfect.
So you only get to hear me once, folks. And as many of my students would tell you, that's plenty.
That's funny.
There we go. Oh, hello, everyone. So we're seeing everyone here. And I will try a comment.
Yeah, try to comment. So Book says it's a tad low, Scott, but not bad. How's that, Book? How does that sound?
Okay. And I'm on there as Astronomy for Educators. So people will know it's really me.
Yes. Yeah, I have to get my mouth right in front of the microphone. So when I pull away, of course, it's going to sound fainter.
Ah.
That's the problem.
Yeah, I got a new microphone this year. I won't promote them, but it works really well. It just sits on my desktop and I don't have to talk right into it. And my students aren't complaining, which is, at least they're not complaining about not being able to hear me. I will lie manfully and say all my students love me. Sure they do. No, it's really one of the nicest things about teaching is that you get to work with some of your favorite people in future tense. Many of my current friends are students from years and even decades gone by, which is lots of fun. And people are saying that your sound is better, which is good.
Yeah.
And I'm getting all ready. I've been prepping my ball of clay for about an hour. And anyone who's worked with school clay before knows that school clay is about the consistency of a wet baseball when you first pick it up. But I cheated. I put mine in a little metal pan on top of an electric radiator for about half an hour before the show. So it's now nice and soft and easily workable, which is good news.
Okay. Well, thank you everyone for showing up today. It's a great Monday, and uh, we're happy to be here. Mike Wiesner says, another Monday.
Indeed.
Where's the thrill of being awake on Monday?
Mondays are lovely.
Yes. Well, hello everybody. It's Scott Roberts and Dr. Daniel Barth from the number four, count 'em, number four. How do you know? And this time he's been working up this oil-based clay, and we're going to create a lunar surface in clay, which
Yes.
is going to be kind of cool. So now I'll tell you a story, Daniel. When I first kind of got into this uh, industry, I was selling telescopes at OPT. It was called OPC at the time. I got a chance to go to the Jet Propulsion Laboratory, and I was so excited.
Very exciting.
And the name of the scientist that was working there will come to me at one point, but he only had a high school education, and he was working at the Jet Propulsion Laboratory, smart as a whip. And he wasn't a high schooler at the time. He was already grown and family guy and all the rest of it. But he was drawing the elevation maps for Mars from the
Wow.
from the spacecraft that had visited there, and he showed me these books. They had these books that were, I don't know, they were about that thick, and there were rows and rows and rows and rows of them, and it was information about each photo that they had taken with the spacecraft.
Oh my gosh.
So this was all done pretty analog still. And
Yeah, back when they were probably typing up the sheets and laminating them and punching them and putting them in a book.
yeah, I think so. But
Golly.
as I recall, they had also built some 3D models of the surface as well, and I think they were probably done in clay, like you're going to do now. So I think this is really cool. And besides, it's a lot of fun to
It
work
is.
with clay anyway. So anyhow, I'll turn this over to you, Daniel.
Well, thank you.
Yeah.
And welcome everybody. This has absolutely been for a number of years my most popular activity. And for those of you that want to know more, of course, you can go on to the explorescientific.com/how do you know, and the activity is available for download. You can write to me at astronomyforeducators@gmail.com. And if you want to go deep, and I hope you do, the Astronomy for Educators book, it really should have been called Astronomy for Everyone, but I wrote it for a class and they wouldn't approve it with that title. So it's Astronomy for Educators, but that's available at the ScholarWorks website. You can find it on any of the activities. It's at the very bottom there, and you can look for it. Scott has a link for it on the How Do You Know page at Explore
Yeah.
Scientific. So today we're going to do how do you know about the moon's surface? And this activity really came out of my experiences as someone teaching astronomy and doing astronomy outreach, working with the public and with students. My students were all high school and college age, but we would often go and take our equipment to middle schools and elementary schools, and my students would do the show. And a reaction we got a lot. We would try to go when the moon was in the first quarter. So the moon is there. It's very dramatic. It's got the nice curved terminator. You can see very detailed shadows in the craters. And you get out these nice telescopes and you get these beautiful views. And somebody would come up and they would look in the eyepiece and they would go, yeah, it's the moon. I've seen it.
Yeah.
And not just snarky teenagers. We're talking adults as well.
Yeah. Snarky adults.
Snarky adults. And this really used to bother me. It still does, kind of, to tell you the truth. Well, I took a lot of trouble. I bought this nice machine out, this instrument that, you know, is better than anything you've ever seen. And it's the moon. I've seen it. And it dawned on me one day, what's happening? And what's happening? Smartphones are happening. Tablets are happening. Computers are happening. Studies indicate that if you're a young person under 25, you're talking 12 hours of screen time a day.
What?
Between video games, television, tablet, phone, you're talking over 12 hours a day, 10,000 or more images per day, and 60% of those can be advertising. So literally in this bombardment of imagery, and people look and they say, yeah, it's the moon, I've seen it. Because it becomes one more image in 10,000 that day. Millions of images a year. The amount research is showing, and I looked this up, and there's some footnotes to this research in the curriculum activity if you want to download it. It's kind of insane, the amount of imagery people see. And Scott, I'm going to include you in the old guy club. When we were kids, you know, did your parents probably limited how much TV you could watch? Turn that off.
We were addicted to television, and back in our era, you know, we were TV generation. You know, you had kids that sat around all day and watched TV. You know, if their parents would let them. You know, so the rule in a lot of people's homes in our generation is you stay outside, you get your homework done first, then you stay outside, and you have to be in before dark.
You come inside when the street lights go on.
Find out where the kids went, you know, in those couple of hours or whatever.
We were told you're supposed to be in when the street lights come on.
Right.
That's what we were told.
That's right.
Go outside and play. Turn the television off. And now you see people sitting down in a nice restaurant, and they're all sitting there at the table staring at a phone. It's not uncommon. And so there's all this imagery. So as an astronomy outreach guy, as an astronomy teacher, my dilemma was, how do you get around this roadblock? How do you make the image that you're giving them more important, more significant, more unique than the images they're seeing on their phone and their tablet and their television and their laptop all day long? And the answer that occurred to me is that, and it should have occurred to me earlier, it's one of those things where you slap your head and go, I should have known that. The more knowledge you bring to the eyepiece, Scott, the richer the experiences and the more you take away. And it's not difficult. It's not strange. It's not a weird idea. This whole idea is that you need to have people in some way bring some more knowledge to the eyepiece. And I'd seen and I'd done, and I hear this a lot from teachers. Oh, you take a pie pan and you fill it up with flour, and then you sprinkle on top with powdered cocoa. I always use black spray paint because it adhered the crust. It made a more regalithy experience. But you sprinkle it on top with powdered cocoa, and then you drop a marble into it, and you get this poof of flour, and you get to see some rays, and that's lots of fun. But that's one crater. And so earlier, I tried an experience where I said, okay, we're gonna do this in a more engaging way. So we took a a cardboard box top from a Xerox case of paper, right? Copy paper. We lined it with plastic trash bag and we mixed up about 30 pounds, plaster of Paris and sand, 50-50,
Okay.
mixed it up, poured it in there, and the sand stiffens up the mixture. And then you spray the top with black paint. And then it's on one of these big plastic painting tarps you put over your furniture when you're painting inside. And every kid picks up a corner and every kid gets a rock. And they all start throwing rocks into, and to make the big craters, I used a slingshot and a rock,
Oh,
kawang.
more
And
velocity.
the plaster splattered and the kids screamed and everybody loved it. And we had lovely different kinds of craters, and we were able to take the big ones and we mixed up some thin black Paris of plaster for lava, and we poured it over and it overflowed into some craters, and we got lots of neat stuff. And you could take string and you could put notches in the side of the Xerox box and thread string back and forth, so it made a grid pattern. Now you've got latitude, longitude, link into maps.
Mm-hmm.
But it was expensive. It was messy, and it
Mhm.
was heavy. You ended up with this beautiful sculpture, but the darn thing was, 24 by 18 inches, or 8.5 by 11 twice, I guess, if you want to be real picky about it. But you didn't want to make another one the next year, because what do you do with the old one? And the custodian is not happy with you if you put a 25-pound plaster sculpture in the trash can for him. That's just not making you fans. So I eventually over time went to clay, and I've got some clay now, and we're going to switch over. I'm working on a silicone mat today, which is lovely for my desktop, and I'm switching over. There we are on my desktop camera,
Yeah.
and I'm working on a silicone mat. If you don't have a silicone mat, if you're a teacher or you're an outreach person, one thing that I often did, I got these cake pans at
Sure.
discount store, and they sell for, I don't know, $1 a piece, something like that, cheap aluminum baking pans. And you can have, if you're doing outreach, you can have your clay and materials in one of these pans and put the pans out on a table. If you're in a classroom and you got the nice Formica desktop, clay's no problem. Little Windex, paper towel, the residue wipes right up. If you're doing this at home, or if you're at somebody else's house, this is not the happy way to do this, because this clay is oily. It's a mineral oil based clay. And if you put it on anything, cloth, leather, paper, the oil will spread out. And if you're on wooden furniture, yay, what a great way to take the varnish off of your furniture. Don't do that, kids. So what I'm going to do is I'm going to basically squash my clay out, and I'm going to try to make a 6-inch square. And you're wondering, why a square? Isn't the moon round? Didn't we just go through that a couple weeks ago? Yes, we did. But we're going to go with a square today, and we want it to be about a 1/4 inch thick. If you're some of my metric European friends, and you're going, what is this inches? What's he talking about? Well, you want to do about 15 to 16 centimeters square. And I'm just going to go ahead and smush this out, and it should be about 1 centimeter thick. And it doesn't have to be perfect. It's not necessary that it's anything like perfect. And when you get it all flattened out, you just flip it over, and you've got this nice surface here. And in just about a minute, you've got a nice, relatively square surface. This is about 6 inches on a side. And is it perfect? Not in any way, shape, or form, but it will work for our purposes. Once again, I want to stress to everyone that this sort of activity, it's not about art. It's not about sculpture. It's not about, it's about engagement. It's about fun.
Mm-hmm.
And we're going to have some fun now. The next thing you're going to want is Some kind of a relatively large marble or ball. And yes, this is a monster. This is a 50 millimeter
Marble?
marble. It's a
Wow.
50 millimeter glass marble. You can use a ping pong ball. It works just as well. I've got a 50 millimeter marble. I've got a 30 millimeter, I think a 30 or 35 millimeter. I've got a 25 millimeter. And then this is the standard size kid marble, just right for swallowing. If you've ever been a little kid playing with marbles, don't
Yeah.
do that at home. This is about a 10 millimeter marble. Anyway, I'm going to start with my big marble, and I'm going to pick an area here, and I'm going to start to roll this. And you see that I'm getting this
You already got the
lovely
crater. Yeah.
kind of circular depression, and I'm rolling it around, and I'm trying to smooth the floor. And here we go. And presto. Scott, what have I just made?
A crater.
A crater. This is actually, and I'm not sure if we're getting a good angle on this, if it's showing up well.
There you
Is that a
go.
little better?
There you go. A little bit better.
Uh,
It is
let me see if I can adjust my lighting in here to make this a little better. Um, is
yeah, it
that
looked like
better?
a snowstorm at first, so
Okay, is this better?
it is better.
Okay,
Better.
let's see if we can make it
Maybe you
even
can make
better
it
yet.
even better. Oh, yeah. Get it
Okay,
make it a little bit dark. A little bit dark.
okay. Uh, so what I've got here is a nice circular depression.
Yeah.
I'm still fiddling with lighting. I'm hoping that's helping a little. Anyway, what we've got is a nice circular depression, and I think I can go ahead and hold this up, and maybe that will be a little easier to see.
Yeah, that's
Okay,
easy.
so we've got a nice circular depression. This is
Mhm.
a Maria. And friends, a Maria on the moon is a crater basin, but this was created by an object about 1/10 the size. So if we're looking at our Maria here, we put a little marble in it. This marble is about the size of the original impactor. It would take about 10 of these across to make our Maria. And so this was a crater made by an asteroid. These things are typically anywhere from 300 kilometers to 2,000 kilometers wide, sometimes bigger.
Oh man.
And these rocks were big enough that they punched through the crust of the moon.
Hmm.
They actually effectively punctured the crust of the moon. We're talking impacts that occurred 3.5 billion years ago. The interior of the moon is still molten. And at this point, with the moon still being molten, lava flowed up out of the interior. And we're going to see how we simulate that in just a minute. The next thing I'm going to do is I'm going to take my smaller 25 millimeter marble, maybe my 35 millimeter marble, and I'm going to make a couple of large craters. And when I make large craters, one thing that people do when they make these is they go, oh, I can't put them on top of each other. That's not true. Craters overlap each other on the moon all the time. There's no rule about no parking your asteroid here on the moon, so you can overlap things. So I've made two large craters, and now I'm going to demonstrate the filling of the crater with lava. And for that, I have a small, by the way, for those who are wondering, this is not quite a kilo of clay to make a model this size.
Mm-hmm.
You can make it thinner and use less clay, but the craters don't always work as well. You can use 500 grams of clay, about a pound if you like. I'm going to take this piece and I'm going to break some off. And I only want a very thin amount. And I'm going to take this and I'm going to, I'm going to stretch this out and I'm going to make this very, very thin if I can. I'm going to press it out here and peel it up and press it and thin it again. I'm going to make this very thin, and we'll see why in a minute. So I'm making this very, very thin. And when I get it nice and thin, I'm going to peel it up and I'm going to lay it down in my crater here. and oh, look, some of the lava flowed over.
Mm-hmm.
And lava isn't nice. Sometimes it's nasty. Sometimes it escapes. And you'll notice here that, gee, my lava in my basin here, the rim is bigger than the lava is. And if you study geology on the moon, you find that often the lava flow is smaller than the basin. And there are times when, oh, the lava has broken through a crater wall and flowed and escaped the Mare.
Cool.
And so we've got this lovely area, and we can smooth this out with our fingers here. And again, I'm using this nice white clay, gray clay, and you don't have to, Scott. You absolutely do not have to. You can use any two contrasting colors.
Mm-hmm.
I've seen in my classroom students using blue and purple and
Psychedelic.
yellow and green. It doesn't really matter, but I like this because it looks more like the moon. Now, in our big craters here, we see that, oh boy, some of our large craters, if we look on the moon, some of our very large craters have what we refer to as central mounts. And so we're looking, what's a central mount? Well, if you think of throwing a rock into a very soupy, muddy puddle, the rock would go down into the mud, and then the mud would splash back up through the center. If you looked at one of these lovely pictures of a water droplet splashing, and so I'm going to take a little piece of clay, and I'm going to put it down in there, and oh, we have a central mount here. And sometimes we get one central mount, sometimes we get more than one. And here I'm going to put a cluster of them, a couple of them in this crater, so you can see what we're doing here. And again, is this great art? It is not. The other thing we notice when we look at Maria is that, in fact, Maria create mountain chains. This is often surprising for people. They think of mountains on the earth where tectonic plates come together and they force each other up because they ram together. The moon doesn't work like this at all. The moon did not have tectonic activity as we know it on Earth at all. And so what happens? We know the moon has mountain chains, the Apennines, the Pyrenees, and whatever. What's actually happening, Scott, is that this giant impact will throw up blocks of stone 3, 4, 5, 8 miles on a side. Oh. And surprise, it's a big mud puddle splash. If you think about a big mud puddle splash, you get this situation where you've got mud puddles splashing, and the splash is circular. The splash is concentric with the whole mud puddle, and you get much the same thing here. And so the moon doesn't take millions of years to make mountains. The moon makes mountains in a minute. If you were there at the time, and it would have been astonishing to watch if you had enough distance. But these mountain-sized blocks of stone, there would be this huge impact, this fiery explosion as this 500-kilometer wide crater is excavated in just a minute or two. And then a minute or two after that, these mountain-sized chunks of stone begin raining down. And some of them make very nice circular patterns, sometimes not. But these are going ahead, and I'll just press them into place here. And again, great art, hardly. But we can see that mountain chains indeed are parallel to the basin of Amaria. And if you think about how they're created, wow, that makes a lot of sense. Well, now that I've got that, I can go ahead and I can take one of my smaller marbles and I can start to make some smaller craters. The interesting thing here, every time you change crater size and make it smaller, you're going to need more. So I'm going to, and we always circle the marble a little bit because that gives us a nice crater rim. And yeah, sometimes things overlap. Sometimes you'll see a series like Aristarchus. It's a series of three craters in kind of a curve. And one of the only things we know is that when we see these sorts of things, we can
Oh,
see
wow.
the sequence
Right.
by what
It's
overlaps which.
lunar every minute here at school.
Right. And the moon is essentially a pristine environment that we look at this and we realize, oh, gee, the moon has indeed, it has no air, it has no water. And because it has no air and no water, well, gosh, surprise, there's no hydrological cycle, there's no weathering. The only erosion is other rocks falling in from space. And of course, most of the rocks are small. The moon and the earth each gather about 10 million tons of material per day, falling in. On Earth, 98, 99% of that burns up.
Said 10 million tons
Tons, metric tons. The Earth collects about 10 million metric tons of space debris every day.
every day.
Every day. And you would think, oh, you would get eating that much, you would get tubby pretty quickly. But compared to the Earth is what, 10 to the 26th kilograms? So 10 million is a tiny, tiny, tiny fraction of a
Dusting,
percent.
right? It's
It's
just
nothing. It's nothing. You know, there are skyscrapers that weigh that much. Skyscraper, Earth, no
sounds like a
comparison.
lot. Yeah.
So you get this lovely thing, and now we start to realize that some of our more modern craters have more interesting features. Some of the modern ones, even the smaller ones, will indeed have isolated central mountains in them. They're usually smaller than the big craters, but they're definitely there. And one of the fun ways to spot these things, Scott, is to go out and look along the terminator, that line between light and darkness.
Sure.
And when you look at that line between daylight and dark on the moon, we're watching the sunrise as the phases change. You can see oftentimes you're looking at the crater and this part is dark, this part is light. And you look and you see, oh, here's this inky circle of darkness. And in the middle, there's a bright point of light. And you realize what's happening is, aha, the sunlight is just broaching the eastern rim of the crater and starting to light up that central peak. And if you were standing on top of that mountain, you would be in the middle of bright sunshine and surrounded by utter darkness for many miles, because the crater beneath your feet would be all in darkness, all in shadow.
So let me ask you a question, Daniel.
Sure.
As an educator, I mean, you know, there are many ways to introduce learning to people. Okay. And if you were just going to read from a book or just make a lecture presentation, but you don't have anything tactile like this, you don't, maybe you got images or whatever. What is the effectiveness of retention of what's going, of what they're learning? How has anybody ever quantified how much better it gets if they're listening to the educator and they're doing something at the same time? Um,
Studies have been done.
mhm.
A hands-on activity alone compared to a textbook reading and answer the question alone, the hands-on activity in terms of retention is about 70% or 7 times greater.
7 times.
Yeah, so retention of just read it. If you're talking a month later,
Okay.
I read it and I answered a couple of questions and I had a quiz and now we're on something else. The retention is below 10%. Hands-on activity after a month is over 70%.
So if you really wanted to know, let's just take, Copernicus crater or any of the craters. Pick your favorite crater on the moon.
Right?
Observe it through a telescope. Maybe draw it, okay, and then maybe try to actually make a model of it. I think that you would learn many. I mean, you would just become intimately much more familiar with this crater and all of its features if you did that.
I would agree. There's nothing like hands-on. The other unique, let me switch my camera back since we're chatting. The other unique thing, and I'm kind of in the dark now because it's easier to see the model that way.
Right.
Um, the other thing that we find, oh, I can see the Terminator on my head. That's great. I have a window over my left shoulder here.
Gotcha.
The other thing we find is that in a diverse classroom,
Yeah.
and this goes for outreach as well, um, we have ESL students, we have students who are not fluent in English, we have students who aren't fluent in academic English in a particular subject. I always used to tease my students. I said, I speak NASA, you don't. But it's okay. What I found is that when you do a model of this sort, and I have a finished one here I can show on camera. When you do a model of this sort, every child, every person at the outreach event does this in their own language, in their own head.
Mm-hmm.
And you're saying, crater, Maria, marble roll, and you have some child who's, just come into the country. Parents have moved from Saudi Arabia, Korea, Mexico, wherever,
Mm-hmm.
and they're not fluent in English. They maybe have very little, but they're saying, oh, this is fun. I'm playing with clay. And, you're talking blah, blah in your language. Imagine yourself going to, say, Germany or Russia, where you didn't speak a word of the language. And somebody says, oh, you're Scott Roberts, come do this astronomy activity with us.
Right.
And they would kind of be motioning and waving and pointing and
Right.
gesturing. And you would follow along good naturedly. And these children do, and adults at outreach, they do too. And we give them the experience first, and then we go back and we say, and this is a Maria, and these are craters, and this is a central mount. And oh, look, we have mountains. And we can use other picture resources to help them. And they start picking up the vocabulary, and now it means something
Mm.
because they have an experience first. If you give children, I remember being in a Spanish class, and here's 20 vocabulary words for Friday's quiz. And you would repeat these, and I had flashcards and the whole banana. And yet, in southern Wisconsin, with no one to speak Spanish with, this went whoop in one ear, out the other, ba-bing. And learning that vocabulary with no experience to go with it was a chore. On the other hand, if we use what I call an experience first method, then we go ahead and we give people, young or old, an experience first. And then we say, okay, now let's give you the language to allow you to express what you know. The central problem for teaching, especially in the standards-based environment, Scott, how do you know the test is digging out all the knowledge? How do you know the test really reflects what this child knows? And the shakier a child's grasp of English is, the more problematic this is. Mentor once told me the first thing you're testing when you give a test in English is whether or not your student understands English. Doesn't matter what the subject matter is.
Sure.
And so our job as teachers, as well as outreach, as well as homeschool, is to give an experience first and then follow up with language, help our students become fluent to explain and discuss and share what they know. They need to say, how do I know? As much as the teacher needs to say, how do you know? The teacher needs to ask these questions. How do you know? And the student needs to be able to express it and say, this is how I know. And if we give them an experience and then give them language to discuss the experience, then indeed we're giving them a much richer experience. And the retention lasts potentially for years.
Right.
When I put these things up on Facebook and I put these on and I go, oh, we're doing Clay Moon this week on How Do You Know? And I get former students who some of them they were in my class in, 98, 2000. One case, somebody who wrote me was in my class in 1994.
Cool.
They're 40 now and have kids of their own.
Right.
And they said, I remember doing that.
Sure.
And
And that's the whole point
is
of
far
doing
better.
things like this, is
Yeah.
that you want it to be, you want some stiction in that, in what they
Stiction.
learned.
Yeah,
I don't know if that's a technical term, but
it works for me.
yeah,
It works for me. Retention, yeah. If we're teaching children to remember until Friday and then there's a quiz and then forget it because it doesn't matter anymore, that's a really poor educational model, in my opinion, number one. Number two, when the child is done with 12 years of learn, believe, repeat, forget, what are they left with when they leave school? Are they left with anything that makes them a better adult, more literate, more fluent?
they're really not prepared for
No,
their world
no,
that they're entering into.
no,
I don't think.
no, I don't think so either. Anyway, let's see if we can go back and take a look and finish this model up. So I'm going to switch back to my other camera again. There we are. Now I'm going to take a highly technical tool, Scott. I'm going to use a golf tee.
Uh-oh.
You could use a little pen cap. You could use a pointy pencil. I've found if you use a pen or a pencil, the oily clay kind of ruins it. So you don't want it, but golf tees are not metal. They're not really terribly pointy and sharp, and safety first and all that. So what we're going to take a look at now is ray structures. And what's a ray? An asteroid comes down and lands, kablam, and it makes a crater. And on the airless environment of the moon, you're talking cubic kilometers of rock. This is hard to grasp in your head. Cubic kilometers of rock are vaporized into dust. And on the airless moon, everything sprays out in a perfectly concentric splash pattern. If you've ever taken a water balloon out to a parking lot on a hot day and thrown it up high in the air and it comes down and it makes this lovely radial splash pattern. If you take a snowball and you throw it at a brick wall, you get this lovely radial splash pattern. And you get this same thing on the moon. And you'll get some streaks and they all head right out from the center. And some of them, sometimes you'll get parallel ones. And some of them will extend and they'll extend far across Maria and they'll extend in different directions. And when you get the really long, big ones, you also find that you get a finer pattern, what we call an ejecta blanket. And again, this is radial out from the crater.
Mm-hmm.
And sometimes you'll see, oh, this kind of shades over other craters nearby. And again, am I making great art? No. I'm sure there are real art people out there saying, oh my God, he's using a golf tee. You're doing it wrong. It's not about art, okay? It's just not. And I get this lovely streaky ray system, and it looks best if it's nicely parallel. And I usually go through and re-smooth the interior of the crater. And there we go. We've got, I think you can see this now.
Yeah.
We've got this lovely ray system.
Mm-hmm.
There it is. You can see it now. We've got this lovely ray system. The catch is, Scott, of course, that this ray, what we're actually looking at, is a layer of dust. It's maybe a centimeter or two thick. It's very thin. And as a result, the moon does have erosion, rocks falling from space, and rays get erased. And we tend to only see rays from the very newest craters.
Hmm.
We can tell them because they tend to have this very nice, sharply defined crater rim.
So, how old would you say is a new crater?
Um, Tycho is a new crater on the moon with a very big ray system. It extends over 1,000 kilometers from uh, the center of Tycho. That's
Yeah.
maybe between 10 and 60 million years old. There's some speculation.
That,
Somebody did some math and said they thought that the Chicxulub impact, the dinosaur killer for the rest of us,
hmm.
uh, and the Tycho crater on the moon were basically from the same asteroid group.
Oh, wow.
They were peers on the timeline. That is, within a million or 10 years of within each other. Um, a Tycho-sized crater. Many people are familiar with Tycho. It's in the southern. It's right, pretty much in the center of the moon, and it's in the southern hemisphere. Tycho is about 95 kilometers wide, somewhere in there.
Mm-hmm.
A crater of that magnitude on the moon today would kill many people on Earth.
Yeah.
Because when you're talking a crater that big, if you're thinking, okay, 90 kilometers, what's that? For those of us in Northwest Arkansas, that's the entire Bentonville, Springdale, Fayetteville metro area. That's the entire Chicagoland metro area. That's a crater as big as all of Los Angeles. And it's going to scoop out initially about 10 to 12 miles deep. The sides are going to slump in.
Yeah.
And so the crater expands a little bit radially as the sides slump in. It can't maintain that ice cream cone shaped geometry.
Mm-hmm.
But you think about this, you go, oh, okay, 90 kilometers wide, averaging about 8 to 9 kilometers deep. That's what, a couple of thousand cubic kilometers of rock. You know, there are a lot of chunks the size of the Chelyabinsk meteor, the Russian meteor from a few years ago. That was,
Right. I
what,
just.
about 200 or 300 meters, right? Football field
Mhm.
size,
Right.
somewhere in there. And it created something stupid like 100 to 200 kiloton explosion. And you're going to have hundreds of things like that raining down on the earth. Not just one, oh, it happened to blow out some windows because the angle was really low. You're going to have these things raining down vertically and making, uh, you're going to have things that make potentially Barringer crater size holes in the earth all over the earth. So, as much as I've always thought as a young man, as a child, I wish I could see a crater on the moon. That would not be a good day.
You
That
mean
would be a
when it
really,
actually happened in
really
front
bad day. And so once we've got our ray systems and we've got a couple of ray systems, and we can take our smaller, and if you want to get mid-size, you can get little beads, right? Little
of?
2 and 3 centimeter beads.
Yep.
And you can make some mid-sized craters, and these little craters pock all over. And if you look at a lunar atlas, if you look at the moon through a telescope, you will see these small, and by small, these are half-mile to 5 mile craters, right? Oh, just little pinpricks. And you might even, if you have a good telescope, you might even spot a rill system. And of course, what are rills? Rills are basically rivers from lava channels, and you see them a lot in Maria. Uh, One of the Apollo missions, I think it was 16, went to Hadley Rill, right? 16 or 17.
Hadley Rill.
Yeah,
Yep.
Hadley Rill. And so these are these big, essentially dry, and they look like rivers. You have to have a fairly good telescope to see them because they are relatively small. They're only the size of the Mississippi, so they're only a few kilometers wide. And they're not big, tall features that cast dramatic shadows. They're concavities rather than projections. So you have to see them right when the terminator is nearby. And you have to have a fairly nice telescope to see them. But now here we go. We've got this lovely model, and we can compare this to the one I made the week before. And you
Yeah.
can see that, we've got craters with rays, we've got mountain chains, we've got central mounts, we have ray systems, and we have lava flows, all sorts of fascinating things. And this didn't take us very long, Scott.
No.
Nothing. People say, oh, well, how young a person can do this. I've had children as young as 6 and 7 do this and have great fun with it.
Sure.
I've taken it to, I was invited by a local library to go and speak. And they said, we have a children's program this summer. So can you come and do a children's program? And I said, oh, sure. And I'll bring this. So I had, I don't know, I had about 15 pans with clay in them. And each one had a baggie with a couple of different marbles and a golf tee. And I didn't take dark clay because that gets to be a cleanup nightmare. We just did it in one color. And it turned out they were 3 to 7-year-olds. That's what they didn't tell me when they asked. Oh, these are some of these kids are pre-K.
I loved it though.
And so we just paired older ones with younger ones. They all had fun.
Yeah.
They all said, "Oh, and what's the marble?" They said, "Oh, what's the marble?" And I said, "Oh, the marble, darlings, is the asteroid that hits the moon. Did you ever throw a rock into a mud puddle?" "Oh, yes, we've done that." I said, "Well, this is like a rock into a mud puddle, except the rock is as big as a city, and the mud puddle that you get is, as big as a state or a county." And they had no idea how big a city or a county was, but they had the idea, really, really big.
Mm-hmm.
And so we were able to successfully make these models, and people of all ages can do this. The wonderful thing, after you do this, if you do this as an outreach, okay, you've got your telescope set up, and because you've been to plenty of outreach events, it's starting to get dark and people are coming up and tugging your sleeve. "Oh, Mr. Scott, is it dark enough yet? Can we see the moon yet?"
Yeah.
And yes, we're going to see the moon in a few minutes, but first I'm going to pass out these pans and we're going to make these models of the lunar surface. And you can literally, if you're not worried about detail, you can do this in 10, 15 minutes. And telling people, crater, ray, central mount, Maria, rill, overlapping craters. Oh, guess what? The ones on top are younger than the ones underneath. It's like footprints in the snow or the mud. Oh, okay. 15 minutes with this. And then you say, oh, now it's dark enough. Let me point my telescope at the moon.
Yeah, now let's really look at it.
And
You
now,
were talking about Hadley Rill.
right.
Let me just show you this is from the lunar.
There it is.
Yeah.
Ooh,
See,
very good.
That's the Apollo 15 landing site. So
There you
yeah,
go.
we did go there.
We did indeed go there.
Full view of it.
And I feel good about my little rill
Yes,
that I drew.
that's right. So,
And you can see some mountain formations in there, Scott. And you can see smaller craters overlapping bigger ones.
yeah,
You can see the one big crater there overlapped the rill.
look at that one right there. It looks like
Yeah, I'm not sure what that was. A really low angle impact, or that's very, very rare.
yeah.
I'm going to have to go out and see the next time. I'm going to have to look at the location and go out and take a look and
Sure.
see if I can see Hadley Rill myself.
Sure.
So the one thing you're not going to get after you do an activity like this, oh yeah, it's the moon, I've seen it. That has been completely eliminated from people's vocabulary. They go, oh yeah, look at that. Is that a Maria? Oh, that big dark circle, is that a Maria? How big is that? And the intelligent questions start to flow. Oh, look, one crater on top of the Maria. Is that younger? How much younger is it? Oh, look, how come some have mountains and others don't? Oh, is that a ray system, that splattery mark around that one? How come they all don't have that? And
Right.
the brilliant, intelligent, interactive questions start to flow from everybody. So and someone says, damn, no stores open right now, want to get some modeling wax. Yes. You can do this with salt dough. Salt dough, which is
Now, how do
2
you make the
parts
salt
white
dough?
flour, 1 part plain table salt, and 1 part water, I think. Look it up on the web. And you can make this in salt dough and then bake it. And it gets hard and it becomes like a permanent thing. So we can do some other things. And I want to show you something. I'm going to switch cameras and I'm hoping this will work.
Okay.
Here's something, and I like every time we do this to show some fun things that can be done as a GIF, where you can take a cell phone and make pictures, or you can make a movie. And so here we go. I'm turning on my camera's
There
flashlight,
you go. That's cool.
and look what's happening to the shadows now. And it's not showing up very well in this camera at all. Let me see if I switch cameras and hold it up in my hand. It may work better in the better camera. So here we go. I'm picking up a model. I'm using this other one here, but it'll work the same. Okay, I'm picking up this model, and
Oh yeah.
I'm taking this, and you notice how the shadows
There
and
you
here they
go.
lengthen
There you
again, and we
go.
hit detail.
Yep. Yep.
And if you have my office has a big picture window in the west, so this time of day I'm getting sunshine coming in. But if you do this, you can see this lovely play of shadow, and what we're actually demonstrating here, Scott,
Mhm.
is the same thing as lunar phases. We're showing how the shadows change as the terminator rises and runs across, and how we get different shadows. And you can look and you can go, oh, you can make a little movie with a cell phone camera. You can make a series of photographs and turn it into a GIF. And a cell phone, because it's a focused narrow beam illumination, as opposed most flashlights are wide beam, they don't work as well. The cell phone the cell phone flashlight works brilliantly, and you can see the change in phases. And I have some videos like that. I will post it on the Astronomy for Educators and the How Do You Know page on Facebook, so people can see them. And so you can go, oh, this is why craters and things look different throughout the cycle of the lunar phases. The sun's at different angles. What do you think the Earth would look like as the sun rises and sets each day? Oh, you mean there would be shadows from the Alps or the Rockies? Or yes, of course there would. And oh, you mean when I'm standing in Europe and I see the sun coming up over the mountain, that's because the mountain shadow is retreating? Yes, it is. And it would look brilliant and beautiful from the moon if you were there and had a nice telescope. And so these lovely thoughts start bubbling up, and it's no longer it's the moon, I seen it. Anyway, let's play another game. I'm going to switch my model here. I'm going to peel this one up. This clay is a little soft, so hence my nice silicone mat. And I'm going to go ahead and adjust a little bit over here. Let's do some fun math. So I'm going to switch my camera again. Here we are, USB camera. This is working fairly well. Does it work better if I prop it up a little bit? What can I prop with that's safe and easy? Here we go. Let's see. Does that help at all? Maybe a little. Anyway, you see we have a nice Maria here. So how do we, it's irregular. How do we measure the perimeter? Well, one way you can do this is you can take some pins, and you'll notice that I put pins in here, and maybe this is better if I point to them. So I've got these pins here, and you can see them, and they're along the edge. And now I take a pin with some string tied to it, and I go, oh yeah, let's start here. Well, how big is this? Well, I can wrap around, and here it kind of goes in. So I change the way I wrap, and I go in and I go out and I go around. Oh,
Okay.
I've now measured the perimeter. So I can take this string now and I can go ahead and measure it with a regular ruler. Well, clever people will say, gee, Doc, that's maybe not very accurate. You've only used about 8 pins there. So what can we do? Well, couldn't we make it more accurate, Scott, by making more pins?
Sure.
I mean, we do this with just 3 pins if we wanted to, and we get this kind of triangle, and it would be an approximation. But oh, we use 5 pins, we get better. We use 10 pins, we get better. What if we use 40 pins? It gets even better.
Right.
This, Scott, is the calculus of limits. When we shrink the distance between points, we get a more accurate measure of the curve.
I see.
And we can get as accurate a measurement as we want by making the limit as small as we wish. This is the theory of limits. I struggled with this in calculus class. Oh my God.
Here it is.
It took me forever.
Right in front of you.
And here it is. And you can show students the idea that, oh, more pins, more accurate. Okay. Oh, look, when we put in more pins, the distance between them is smaller. When we make the distance, the change between one pin and the next, smaller.
More data points.
More data points. So if I just use 3 pins, I get something like this. And I go, oh, well, 3 pins, that's not very accurate. Well, let's use 5 pins. So 1, 2, 3, 4, 5. Now I've got a little pentagon here, and we go, okay, now it's getting a little more accurate, and students pick this up really quickly and naturally. Oh, what else can we do? We can take an eyedropper, Scott. How many drops of water does it take to fill a crater? The excavated volume of a crater is a very good estimation for impact energy.
I see.
And you can look it up in NASA. Well, how big an impact do you need for certain crater sizes? And you can find that out, and you can relate these. I believe it's a logarithmic scale, but you can just go ahead and say, oh, what's the impact energy of the crater? Let's fill it up with water and see. And since it's an oil-based clay, it just runs off. It's not a problem. Oh, well, can we do more things? Indeed, we can. I'm going to take our model that we made, and I'm going to show you something really fun. And what we're going to do now, let's make an excursion in map making. So here's the model we just made.
Okay.
So let's go ahead and put my ruler down here. I'm using my ruler in centimeters. And I'm seeing I got just about a 15 centimeter thing here. And what I'm going to do, you can actually use dental floss, and you can put the dental floss aside and run it in. You can take a metal edged ruler and you can wiggle it back and forth and make lines. But you know what I found works really great? And as usual, this great idea came to me from a student. They said, Doc, why don't you use a pizza cutter?
Pizza cutter. Okay.
And this isn't a pizza cutter. This is a rotary cutter. But I can go, oh, well, here's a line at 2 centimeters. And I draw it across. And here's 4 centimeters. And I'm trying to make this parallel. And here's 6 centimeters.
Okay.
And you can see where I'm going. Here's 8 centimeters.
Sure.
10, I'm getting a little sloppy now, forgive me. 12, 14, cuts right across there. And then you know where we're going, right?
Right.
And gee, I'm creating a coordinate system, yay. And if you're talking measurement on a globe, you're talking latitude and longitude. If you're talking right ascension and declination in the sky, measuring things in astronomy. And so I'm going across, and normally, if I were doing this in a classroom, I would go ahead and put this on a piece of paper that was marked, And I would put a ruler across, and I would try very hard to make this as neat as I can. But you can see I've got this lovely coordinate grid system. Ooh.
Mm-hmm.
Now, if you're thinking it's a grid system, all right, how big are these squares? Well, these squares have got to be something on the order of, well, what? Make them 2 degrees apiece? Okay. Well, on a moon, sphere that big, how big is 2 degrees? You do the math, right? A little simple mathematics. Okay, if the moon is
Moon's,
3,700 kilometers,
yeah.
is the diameter. And so what's the circumference? And you could go ahead and work out the circumference and divide by 360
Okay.
and get the distance for 1 degree and say, okay, 2 degree squares of this many kilometers. So now you have a scale. So how big is my Maria? How big are these craters? Right?
Right. Right.
And you can put 2 pins in and you can say, gosh, if I have 2 pin locations, how far is it from this crater to this crater? And now you can, of course, go ahead and take your string and you can say, well, Pythagorean theorem, right? Because we can go ahead and we can put another pin in here and we can say, oh, can we do Pythagorean theorem? Sure we can. Here we go. Right?
Yeah.
Hypotenuse a squared, b squared, c squared.
Okay.
And see how far apart is this? And you start to get a feeling for how big my landscape is. All right. What's the perimeter? If this is our scale, what's our perimeter, not just in centimeters, but in kilometers? What's our true scale? How many kilometers per centimeter on our clay map? And we look and we say, well, all right. Not only you can do distance, you can do area, you can do perimeter, but you can even go farther than that, Scott. You can do fun. And this is for older or more experienced students. You can actually go and say, well, all right, let's do some map making. So we have this over here. Let's move this and let's go ahead and take a look at this right now.
Okay.
There we go.
All right.
Excuse me while I move things around. Now you can see what I've done here. I've actually taken a piece of construction paper and my squares on my moon map were 2 centimeters. And these, I think, are, yeah, they're 4 centimeters. So I have a map that's bigger than life-size scale. And I just go ahead documenting what's in each square as I go along. Again, this doesn't require great art. Oh, this one is split between 2 squares. Well, you sketch it in. And I sketch these in pencil, and then I go over them in ink. And you see I have some features here that are dotted lines for, oh, that's a very eroded old crater. I have my little icon for mountains, and here they are. I have ray systems, and I've drawn these very nicely. And then I went ahead and I said, oh, let's come up with a naming system. I did mine the way the moon is really named. I used basically, I have a key for features.
Okay.
Here's a crater, ejecta, central mount, mountains, Maria, rill, ray system, eroded crater rim, and crater chain. And then I had, what's my, Mariquelum, the Sea of Heaven. And then I have, crater Boardman, crater Eichmann, crater Schwabel, crater Kern. And if you're not recognizing these, teachers who were important to me in my youth.
Okay. That's
now,
cool.
I have students go ahead and do this, and I say, okay, let's make a map. And, well, I'm not good at art. You don't have to be. You just have to copy what's in one square.
Sure.
You copy one square at a time, and you do it in pencil and kind of square it up. Is it perfect? No. Does it matter? No. You're basically having adventures in cartography. And, okay, kids, make up a naming system. Astronomers are famous for their naming systems. That's why Uranus is not named George. You know that story, of course. Herschel, the German British astronomer,
Right.
wanted to name the new planet after his patron, King George III, and so he said, "We will call it George." And everybody said, "No, no, 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 that's not a name. It something." And I like the Greek version of the name, Uranus, as opposed to the Anglified version. And we've heard all those jokes.
Uranus.
So
Yeah.
let's consider them told, and I won't even bother.
Yeah.
Uh, and so, and the International Astronomical League has gotten so dictatorial about this. You can't discover a new asteroid or planet and name it what you want. They have to have a name that's approved by a committee. I don't like that much, but there we go. It's not my world. I just live
We're
here.
living in the wrong era,
I guess. Remember in November, Barth for Emperor, and I will solve all these niggling little problems.
Yes.
There we go. Solve all these little problems for you. Don't do that. I would hate the job. I would run away. But basically, in this fantasy world exercise, kids do, oh, can I name them after rock bands? Can I name them after cartoon characters? Can I name them after Disney princesses? Of course you can.
Sure.
Anything you like. Flavors of, I had somebody do flavors of ice cream. I'm like, really?
Nice.
Yes, because the ice cream store is my very favorite place. I'm like, there you go. And so, and if you go to if you look at a map of the far side, gee, guess what, Scott? Instead of being mostly Western scientists and mathematicians, it's a lot of Russian people.
Russian ones, sure.
And Slavic names, because they were the Lunik probes were the first to photograph the far side, 67, I think. So we have the Moscow Sea and all sorts of different things. There's some American, the Apollo named craters, I believe, are on the far side. But so there you go. Lots of interesting things. You can expand this activity. You can do it as a simple, gee, here's a pie pan. So you can go to an outreach event and you can say, okay, guys, here's a pie pan, here's a lump of clay, and here's some marbles and a golf tee, and pass these out, and everybody sit down on the ground, and we're going to make a lunar surface. Right. You could do it as a 10-minute activity as an outreach. You could spend a week on this in a classroom, going from one hands-on activity to the other.
Easy.
You can go as
about the moon and how it affects.
Oh yeah.
Us,
and we'll cover some of those things in upcoming episodes. The moon is a wealth. You could have a whole astronomy course just on the moon and the Earth.
Yes, you could.
But you can. I purposely don't go very deep into the math here. I mention it and I chat about it. My assumption is that people who are there with the math will know how to add it in. They will know how to. And of course, if you have questions, you're welcome to email me at astronomyforeducators@gmail.com. I'm hoping everybody listening tonight, if they haven't already done so, will go to their favorite search engine and put in Astronomy for Educators, Daniel Barth, or go to the explorescientific.com/howdoyouknow and find the link and download the Astronomy for Educators book. We are in about 4,400 schools. So in the month we've been on the air, Scott, we've added 1,000 more users to the book, to the Astronomy for Educators community, which I'm so thrilled with.
That's great.
And more than 50 countries now, where we have people using this as a resource for teaching. Public school, private school, homeschool. Almost everyone, 78% of the people who respond, and there's a survey link there. I hope you'll take the survey. 78% say, you know what? My school provides me with little or no materials for hands-on. And they really appreciate that this is, almost cheap as free. You could do this in Salto for literally pennies. Almost every school I know of, somebody on campus has clay, right? It's in the art department. It's in the biology department. Somebody has a big old box of clay. And if you're homeschooling, you can get a couple of pounds of clay for cheap. If you go get the really cheap clay,
the salt dough. You know,
yeah, there you go.
make the salt dough.
There you go.
I just posted instructions on how to do it. So
There you go. The salt dough
it's
is
easy.
very
Salt,
inexpensive.
flour together, stir in water, mix well until it forms.
Most of your hobby stores have clay. Amazon has clay. I recommend against the brightly colored clays. I've had students come in, I got red and green, and they had Christmas colored hands because cheap clay uses cheap dye. That's one nice thing about gray and white clay. There's very little dye to come out on your hands, and good quality clay will not stain your hands with color.
How about
But if
Play-Doh?
you get the cheap stuff, you're probably better off using salt dough.
Yeah.
So I've had fun tonight, Scott. I hope everybody else has too. Next week, we're going to kind of take a different track. We've all heard the story. Newton sitting under an apple tree in the cool of the morning and looking up at the waning moon up in the sky, and the apple falls and bonks him on the head, and he looks at the moon and says, aha, gravity, orbits, it's obvious. Did you hear that story in school, Scott? Newton's apple.
Yeah, sure.
Very famous. And of course, if you were an irksome little child like I was, and you raise your hand and say, but how did he do it? How did he figure it out? How does the apple falling make the moon in orbit? How does it work? How do you know? We don't have time for that now. It's so obvious.
We don't have time for an
This is a silly question. If you don't know, I'm not going to explain it to you.
Yeah.
It's one of the greatest intellectual leaps of all time. If we forgot about everything else, the intellectual genius of the apple and the moon would secure Newton's place in history for all time. And so next week, Scott, we're going to go look at the apple. Perhaps we can I would love to have next week, friends, if there's some of you out there who would like to come on the show live and interact with me, talk with me, maybe do the demonstration on your own and comment. We'd love to have you. Send us an email, astronomyforeducators@gmail.com, and I will forward it on to Scott.
Yep.
We'll contact some people. I would love to have a circle of friends because, playing with toys is fun, but playing with toys with friends is more fun.
Yeah.
So I would really love that, and we'll try that for next week. And maybe it'll be something we do routinely, maybe every once in a while, but we'll see how it goes. And I hope we'll see you here next time on How Do You Know?
Thanks, everyone. That's great. Thank you, Daniel, and thank you to the audience for watching today. We have two very special episodes coming up tomorrow where we have Dr. Chris Impey from the University of Arizona, and we're going to be covering one of his books of his journey to northern India, where he teaches science and cosmology to Buddhist monks. So,
wow.
And he talks about the differences in cultures and how to get Western scientific learning into an ancient culture. So it's very interesting. And then we have our 40th Global Star Party with our guest host, Dr. David Levy. So really looking forward to that. Should be a terrific day tomorrow, and as it was today. And so thanks very much, everybody. And we'll see you next Monday, Daniel, on episode number 5.
And I will have the new activity will appear quickly on the Astronomy for Educators page, and I'll get it off to Scott as soon as it's done, and it'll be on Explore. So grab that, take a look, and if you want to join me, send me an email. It'll be exciting to have some friends.
Thanks.
Thanks, everybody. And thank you, Scott.
Take care. Bye-bye. Hello everybody, this is Scott Roberts from Explore Scientific, and today I want to talk about the world-famous Galileo Telescope Kit. This is a kit that you assemble by yourself. You'll learn how optics work by assembling the objective lens and also the eyepiece. And there's two different eyepieces that are in this. A 25 power, 20 millimeter eyepiece, but it also comes with this very clever little device here that works both as a Barlow lens that will double the magnification of this eyepiece, making it 50 power, or it can be used also as a Galilean eyepiece, which gives 17 power to the telescope. This is what Galileo virtually saw through his own telescope. So you can have that same experience that Galileo had looking at the moon, looking at Saturn's rings, looking at Jupiter. It is a telescope that was designed for the International Year of Astronomy in 2009. And it's a fantastic kit, both for child and adult, to learn how a telescope works. And so if you get the telescope like this, you can either have it on a stand like this, you can hand hold it like a pirate's glass, or on the bottom here, we have a threaded hole here that you can put it on a camera tripod. Very versatile, very rugged, and a lot of fun, all from Explore Scientific.